So there we go. That's the vector we're working with. Now that we know how to construct it, that it is possible to encode your text in the version of a vector. For understanding purposes, we're not going to work with the vector. We're going to work with the text. So we're going to create our neural network working with the text, but just keep in mind that in a machine sense, we do need to work with numbers, and it is possible to construct that vector of numbers from our email. And the vector of numbers will be about the same size as the email itself, except it'll have the SOS at the start, EOS at the end. And the other thing here is you can see we dropped the SOS because it's not that important. Every sentence will always start with the SOS, so it won't make any difference if we feed in the SOS at the start or not. So we're not going to even bother with it. We're just going to keep these. EOS is important, as we will see why just now. It's important because it will dictate when the output will terminate. Okay, so basically what we're doing is we're feeding these values into our recurrent neural network. So as we discussed here, we've got so this value goes into our first element of our recurrent neural network, into first layer, and then it feeds into here. So we'll talk about this in a second, how this works. This is just a classic recurrent neural network, but we'll mention LSTMs as well just now, as you will see. But for now, just imagine this is a classic recurrent neural network feeding into itself through time as a timer. Also, we're adding new information, like some information. We've got an output. We've got like a memory cell. So it's feeding into itself. Plus, we're putting in a new input and so on. Then here we're starting to see an output. So as soon as we have the end of sentence, that's over here. That's when we're going to revert to that structure that we talked about. So if I jump back up a couple of slides, this one, as you can see, we're feeding in. As it ends, then we start to see the output. That's the architecture that we're creating. So here we got the output, then it's feeding into the next element. Then we got the output, next element, output, next element, end of sentence, and that's it. So let's discuss this in a bit more detail. As you can see, here's the text of the email. Hello, Kirill, checking if you're back to Oz, back to Australia. And so the ideal response is like, yes, I'm back, end of sentence. That's what we're aiming for. This is our ideal scenario. How we're going to train it, we're going to talk about that in the next tutorial. For now, we want to understand the architecture that will facilitate this ideal scenario. So what happens here? We've got all the inputs. So as it's a recurrent neural network, we're able to feed in whatever number of words it can be. In this case, 1, 2, 3, or comma 3, 4, 5, 6, 7, 8, 9, 10, 11 words, including commas and full stops, and 12 including the EOS. Or we could feed in an email which is like 1,000 words long. Same approach, just the number of steps would be longer. And then once they're processed, we want to start getting the output. So this will be like a parameter in your algorithm. You'll see that. So this will be a parameter in your algorithm which would relate to, would be adjusted to the length of your input, which is your email. It would be a variable input, and that's exactly what we're after. And then once that's done, the network is going to start predicting approach. So how does this work? How does it know that it has to have like 4 outputs? Why not 3? Why not 5? Why not 10? Well, the way it works is with every step, starting when it starts prediction, and again, it's totally up to us to say when we want it to start predicting, and the way we're doing it is as soon as this input is over, that's when the predictions happen. So this first prediction, in fact, in one of these predictions, there's 20,000 options, 20,000 possible predictions or 20,000 possible results that the network can pick. So let's start with this first one. Here, once all of this has gone in, it needs to make a prediction. There's 20,000 variants. So the way the neural network will do, and again, we're not talking about training right now, we're talking about the end result. The end result is the neural network will spit out a probability score for the options that it has, and so it'll assign probabilities to the different words that it can pick from A to apple to antenna to all the way through to Z, zebra, and whatever other words there are in between. So it'll assign probabilities, and basically we will know that it'll analyze all the words and it will pick the one with the highest probability. So in this case, it's yes. The word with the highest probability was yes. Out of the 20,000, that's the winner. Then residual information from the network is propagated forward. In here is passed on to the next cell, and here the next one that is picked is I'm. Here next one's picked is back, and here next one that is picked is end of sentence. So end of sentence, as you remember, is one of those 20,000 options, and as soon as end of sentence is picked, that's when we know when to stop. So it could have been longer, it could have been shorter. So here it's not up to us, it's actually up to the network to generate the right response, and hopefully you'll know how to do that based on the training that it's been. And we'll talk about the training again in the next tutorial. So once the response is generated, bam, once the EOS is generated, this whole thing ends. Something to note, sometimes, if training was done well, there will be an EOS. That just means it understands that sentences need to end at some point. Another way you could do it is you could have a limit. You could say not more than 50 words in the reply or something like that, and then cut it off. So that just doesn't go forever. So here's an example of an LSTM image. And again, this is from the RNN information. And so here it's a type of recurrent neural network. And here what is happening, why I brought this up, is because in an LSTM you can see we've got that part over here, the memory cell, but also in an LSTM we're feeding back, as you remember, we're feeding back the value. So this value that we have, or here is better, you can see the value that we're outputting up here, we're actually feeding back into the network. As you can see, that's not happening here. We just have the memory going ahead, the memory cell, that top one. Like in comparison, you can see that there is a memory going through, but we're not feeding this output back in. So that's what we're going to fix. We're going to take this output and feed it back in. So yes is the output, but also it's going to go in here. So essentially we're using an LSTM network over here to make sure that we're taking into account not just the memory that's flowing through, but we're using the output that we generated before, and that will help the network understand the meaning. So it just works better this way. It just can create better sentences like that because it remembers not only just the overall memory that's been passed through the network that is updated through these cells, but also because it remembers the immediately preceding word and helps it formulate better sentences. So that's our architecture. That's how we're going to construct it. So over here we've got our cells. We're feeding in the information, creating that cumulative understanding, creating that vector of meaning for us. So by the time we get here, we've accumulated the whole vector, and this is going to be the meaning of the sentence is basically contained in this cell over here, and from here we're starting to extract the answer, and that's why these parts have their names. Encoder, so we're taking all of this information that we have at the start, we're encoding it into this one cell, and then we're decoding it or providing a response through this part. So this is the encoder, this is the decoder. So that's the overall kind of overview of the architecture of a sequence-to-sequence model. It's got a first part that encodes the meaning, Then it's got a second part that decodes the answer from the encoded meaning through, and both of them work through an RNN. So basically we have two recurrent neural networks attached to each other here. Of course, this is a very basic example, and like I know it's quite complex now, but once we talk about the training in the next tutorial, hopefully it'll become a bit more intuitive how this works. But this is the architecture, and again, this is a very basic example because in reality they actually you can make them deep. You can make them deeper than that, and the way it works is something like this. So to encode that vector of meaning, you have layers of recurrent neural networks. And then once that's done, then you start decoding. So they not just feed into each other, into themselves, they feed into the next layer, into the next layer, and so on. And as we know, like more neurons means more flexibility for the network to assign different tasks to those neurons, assign different roles, and encode the meaning better and understand. Basically, in human language, means understanding the sentences better. All right, so that was the sequence-to-sequence architecture. I know it's quite a lot to take in, but bear with me. In the next tutorial, we'll talk about the training, and of course, then once you're going through the practical tutorials, all of this will come together. Once you have your hands on it, it'll all make sense how you're building. Once you're able to actually construct it and set the parameters, set the architecture, all of this will come in handy. So don't stress out if there's some parts that are still a bit vague. It will all come with time. It's definitely a worthwhile investment of time to have gone through this tutorial. And on the next tutorial, we'll talk about the sequence-to-sequence training, and I look forward to seeing you there. Until then, enjoy natural language processing.